Uniform and non-uniform electric field. Uniform electric field. If the magnitude and direction of the electric field intensity remains constant throughout the region, it is said to be uniform electric field. If the magnitude and direction of the electric field intensity varies from point to point, then the electric field is said to be non-uniform electric field. Here we can see that in this region, electric field lines are closely spaced. At this region, the electric field lines are widely spaced. So this electric field represents non-uniform electric field. If a charge Q is placed in this electric field, it will experience a force F is equal to QE, and because of this force it moves in the electric field. If the charge Q placed in this electric field is a positive charge, it moves in the same direction of the electric field. If the charge Q placed in this electric field is negative, that is minus Q, it will experience a force F is equal to QE, and it moves in the opposite direction of the electric field. We are going to learn on a system of two charges, that is electric dipole. A pair of equal and opposite charges separated by a small vector distance is called an electric dipole. An electric dipole consists of two equal and opposite charges that are infinitesimally close together. Although real dipoles have separated charge. The line connecting the two charges is called an axis. The line perpendicular to the axial line is called an equatorial line. Examples of dipole in the molecular level are water, ammonia, hydrochloric acid, etc. One important term related to dipole is dipole moment, P. The strength of the dipole is measured by dipole moment. You already know a dipole consists of two equal and opposite charges separated by a small distance. Let Q be the charge and 2L is the distance between the charges. Then dipole moment P is equal to Q into 2L. The length we are considered as a vector. It is from negative to positive charge. So dipole moment is also a vector. It is pointing from negative to positive charge. Its unit is coulomb meter. We already learned electric intensity due to a single charge. Now we are going to learn electric intensity at a point due to an electric dipole. That means a system of two charges. Electric intensity at a point on the axial line due to an electric dipole. You know, this is the axis, and if you're extending this axis, this is the axial line. Consider a dipole AB. P is a point on the axial line of the dipole where the electric field intensity is to be determined. The length of the dipole is 2L and the point P is at a distance r from the center O of the dipole, and the point P is at a distance r minus L from the positive charge and r plus L from the negative charge. The electric field intensity at P due to charge at A, that is the negative charge Q, is given by the equation 1 by 4 pi epsilon 0 Q by R plus L the whole square, and it is represented by the vector EA. It is pointing towards the dipole. Electric field at P due to charge at B, that is the positive charge, is given by the equation 1 by 4 pi epsilon 0 Q by R minus L the whole square, and it is represented by the vector EB. It is pointing away from the dipole along the axis outward. This figure, you can easily understand that these two vectors are opposite to each other. So the net electric field at P is equal to EB minus EA. You already know EB is greater than EA because positive charge is near the point than the negative charge. So that vector is greater than the force due to charge at A. The net electric field at P is equal to EB minus EA. Substituting the equation 1 by 4 pi epsilon 0 Q by R minus L whole square minus 1 by 4 pi epsilon 0 Q by R plus L whole square. We can take Q by 4 pi epsilon 0 outside. It's a common factor here. So Q by 4 pi epsilon 0 into 1 by R minus L whole square minus 1 by R plus L the whole square. The resultant electric field E is equal to Q by 4 pi epsilon 0 R plus L whole square minus R minus L whole square divided by R square minus L square the whole square is equal to Q by 4 pi epsilon 0 R square plus 2RL plus L square minus R square minus 2RL plus L square divided by R square minus L square the whole square. While removing the bracket, we can cancel some terms like R square minus R square, L square minus L square. So the equation becomes Q by 4 pi epsilon 0 2RL plus 2RL divided by R square minus L square the whole square. Q by 4 pi epsilon 0 into 4RL divided by R square minus L square the whole square is equal to Q by 4 pi epsilon 0. 4RL can be split into 2R into 2L by R square minus L square the whole square. You already know Q into 2L. Q into 2L can be taken together by 4 pi epsilon 0 into 2R by R square minus L square the whole square. Comes P by 4 pi epsilon 0 2R by R square minus L square the whole square. You already know the distance R we consider is very greater than L, or if the distance L is very smaller than R, so L can be neglected. When you neglect the L from the equation becomes P by 4 pi epsilon 0 2R by R square the whole square. The equation becomes P by 4 pi epsilon 0 2R divided by R raised to 4. The electric field intensity E is equal to 2 into 1 by 4 pi epsilon 0 P by R cube. The resultant electric field is along the direction of the dipole moment. From the equation, we can say the resultant electric field E varies inversely proportional to the cube of the distance. For a single charge, the electric field E varies inversely proportional to square of the distance. In the case of a dipole, it varies inversely proportional to cube of the distance. It means electric field varies faster than a single charge.